Hello everyone, welcome back to my channel. Today let's go over a premium medium question that I just solved on my own a couple minutes ago. So I'm really happy about this because I came here shortly after solving best sightseeing pair and I was able to quickly recognize the pattern and come up with my own solution without any assistance. So again, pretty proud of that. So I just want to show you how I did it. So basically the question itself is not too hard. You're basically given two integer arrays of the same length. So you want to count pairs of indices where this plus this is bigger than, say, this plus this. Not true in this case, but if it was, that's what we want to do. And we just want to return an integer denoting how many of those at the end are valid. So obviously the brute force approach is just to go through n squared for j in range I plus 1 length of nums of 1 because j has to be bigger than I. So then we can just say if nums1 of I plus nums1 of j is bigger than nums2 of j of I plus nums2 of j, then we just increment it and then we can return it at the end. So that obviously works, but this is n squared because of the nested loop, so it's going to be a little too slow. So let me show you the solution that I came up with, which is took a kind of a little bit of observation, but so here, okay, let's try to figure out what this equation means. Let's copy this here. And so what does this mean? Well, we want to find I plus j, I plus j. So a pair in both arrays. So if you make some observations, let's say you try to find nums1j, then you can just kind of subtract this here and you get minus nums1 of I, and then you find nums1j, but I find that that gets a little bit too complicated. So what I like to do is just to run some simulations. So for example, let's say nums1i is 5 and nums1j is 1. And then here, let's say we have 1 and then 3. 1 and 3. So if we notice what the difference between these 5 minus 1 is 4, right? And then 1 minus 3 is negative 2. So this minus this, and then this minus this. We want this to be bigger than. So what that means is that as long as we add this kind of a difference to this and it's bigger than 0, that means it's a positive difference because 5 minus 4 minus 1 is 4, 1 minus 3 is minus 2, so 5 plus 1 is 6, this is 4, there's still a difference of 2, 4 minus 2 is 2, and that's bigger than 0, so that's okay, right? So if you think about this minus this compared to this, everything to the right of the current minus itself, so the current index in nums1 minus nums2, then this becomes easier because you can just calculate this. And so we want to find that number that, you know, at least is bigger than 0 when you add that difference to the current difference of I, right? So if you know that, it makes it a little easier. So let's go ahead and say current, and we're just going to go through nums of 1, and let's append the difference, which is just nums1 of I minus nums2 of I, right? So 5 minus 1 in this case. And then now we can just do this again, right? So the current difference is just this minus this, nums1 of I minus nums2 of I of j, or I, and then we have to find something to the right. So let's print current difference and then current of I plus 1 to the end. Cool. So now what that means is that, again, if we have to add something, we have to make sure if we add it, this is 2, it's bigger than 0, that's fine. 1 plus minus 1 is not bigger than 0, so there's only one pair here. Here, there's 0 pairs. Here, there's 0 pairs. So in total, there's 1 pair because this doesn't even have anything to the right of it, strictly to the right of it. So now that makes it easy because what we can do is just run a binary search. So, or the easy way to do this is just to say, okay, we're just going to count if current difference plus A is bigger than 0, then that's a new pair, right? But that's the core idea, and then we can just return answer at the end because everything to the right is valid in that scenario. But this is still n squared, and this is recreating the list, so I'm going to show you what I did instead. So it's still moving. Okay, so instead of doing this, we want to find something that when you add it with this one, it's bigger than 0. So let's say that the current difference is 6, right? Well, anything plus 6 that's bigger than 0 means has to be bigger than -6, right? Because 6 plus -6 is exactly 0. 6 plus -7 is -1. That's the opposite direction we want, right? So find something in the right that is bigger than the negated version, right? Because every element is positive. So that makes our life a little easier. So what we can do is, instead of this, we can run a binary search and we can turn this into a sorted list. And then, because the current difference is going to be in this list, right, from the beginning, including what? This is supposed to be 1, -1, 1, -1. That's how this current list looks at the beginning. And then, so we're just going to discard the current difference. And if we print curdiff and SL, cool. Now they're in sorted order. And then just to make sure that we're clear, we want to make sure that these two are the same things, except this is just in sorted order. So that looks right. That looks right. This is the sorted version of this, vice versa. Okay. So now then we can say, okay, 6, we want to find something that's bigger than -6. All of them are. Okay, so then we would include 2 additional pairs in this iteration. So we can, to find something that's bigger than the negative current difference, we do a bisect left inside of SL, and SL is everything to the right. So we want to do negative current difference. So let's print SL, let's print curdiff and SL and BR. So, okay, 0. So the total length minus 0, so that's 2 additional pairs. This is bigger than -5, so that's 1 additional pair. There's nothing there. So instead, we can just say answer plus equals to length of SL minus B right. Okay, so that gives us everything bigger than the negative counterpart of current difference, which is going to be positive. So, okay, so let's see here. It's bigger than this, so let's print BR. So it's bisect right. Find everything bigger than it. Okay, so 2, that's good. So 3, there's 1 that is bigger than the negative counterpart, which is exactly -1. And then let's submit this. Okay, and submit it. And there you go, passes all test cases. Again, I'm really happy that I solved this on my own without any assistance, although it's not the most efficient in terms of runtime and memory. I'm sure you could optimize this a little more, but just to show you the core idea of using binary search in this case. And so, yeah, hopefully this wasn't too bad. So thank you for watching and stay tuned for more.